Okay, so good morning, everyone. So let's start the class today. So today, I hope it will be a relaxing class. So we are not going to talk about something that is super serious, but we are still working on examples on induction. So this is the first example that I want to show you. So we are looking at this kind of a game. It is a game, a solitaire game, which is played by just one person, and it involves some peg. So peg is some chess piece, some piece. Okay. So here, so imagine you have a very, very large board, a board that has infinite size. Okay. So it is a grid. Okay. So you can see that. So it is like a Go chessboard, or it is like a Othello or reverse chessboard. So you can place, but here you are placing pieces in the square inside. Is that okay? Now, suppose that originally, this is the original configuration, that you have 4 pieces here, arranged in a square, 2 by 2. And then in this solitaire game, we can move pieces around, such that if there are 2 pieces adjacent to each other, and there is an empty square adjacent to them, either on this side or on this side, if this is the case, then this piece can jump to this location such that the piece in the middle that is jumped over is taken away. Is that okay? So if I jump this piece here, then we take this away, and then this piece becomes locating at this location. Is that okay? So we can continue the process. Like let's say this time we choose this piece and jump over to this location, and then in that case this piece is gone. And then here we have 2 pieces left, and then we are going to jump this one over this one, so that this one is gone, and then we have just one left. Is that okay? So in this solitaire problem, we are asking if it is possible to start with some configuration like this. There are 2 by 2, and then in the end you just have 1 piece left. Is that okay? So here let me emphasize a little bit about the rule. Okay, so it must be like a piece jump over another one, occupying the position immediately touching to this. So you are not going to jump. So for instance, I cannot jump this one to this location and take away this one. Is that okay? Every time it must be jumping 1 piece. Okay? And there is another rule. So for instance, so this is to emphasize the rule. So if this, let's say this location is occupied, then in that case we cannot jump over it. It is because I need to find an empty space to accommodate this piece. Is that okay? Is that very clear? Okay, good. So we are going to show that, okay, so this problem has 2 parts. One is easy, the other is difficult. So the easy part is, if you are given the initial configuration, which is an n by n square. So here it is 2 by 2, such that n is not a multiple of 3. N is not a multiple of 3. Then this game can always finish with 1 piece. So we can finish the game one piece. Okay, is that okay? So this is the easy part. And then for this one, we can show this by induction. Okay, so we are going to do this today. And what is the difficult part? Now the difficult part is we want to show that if n turns out to be a multiple of 3, so let's say 3 by 3 or 9 by 9 or 6 by 6, then in that case we can never do that. Okay, and for that one, the proof is more complicated, and it is by proving by contradiction. So I will skip this for today. Okay, and if we have time, we will do that. Okay, so how do we solve this by induction? So what are the base cases? 1. Very good. 1 is the base cases. 1 is the basis case. So 1, you start with 1 by 1. So can you finish the game with just one piece? Yes. Excellent. Actually, for this problem, there are 2 basis cases. Okay. The other basis case is 2 by 2. So you will see why we have two basis cases. Okay. So 2 by 2, we can also finish with just one piece left. This is the solution. So we have found a way. This is the witness. This shows that 2 by 2, you can finish with just one piece. Is that okay? Now, suppose that, so here, this induction argument is quite interesting. So what we are going to show. So let's say, so this Pn is the statement that we can finish with one piece when we start with, so when we start with n by n. Okay, so n by n pieces, it is not n square pieces in arbitrary location. This is n by n in the square form. And then we have just shown what? We have just shown that P1 is okay. And then we have also shown that P2 is also correct. So they are all correct. Is that okay? And now what we are going to show, okay, we are going to show that if P1 is okay, then which one is okay? Let me see. Then P5 is okay. Interesting, okay. So it is not like 1 go to 4, it's 1 go to 5. So we are also going to show that if P2 is okay, then P4 is okay. Actually, in general, okay, in general, we are going to show Pn, let me see, okay. So if a number is of this form, 3k plus 1, so like P1, then we are going to show that it is correct when we are adding 4 to it. So we are going to show that P3k plus 5 is okay. On the other hand, if we know that 3k plus 2, if a number of this form, this is a multiple of 3 plus 2 is okay, then 3k plus 4 will be okay. Okay, so this is what we are going to show. And why this work? Okay, so let's take a look. Okay, so so we have 1, 2. Okay, 1, 2, 1 will imply 5, 2 will imply 4. Am I correct? Okay, and then 4 will now imply what? Imply 8. Is that okay? Is it 8? Yes. And 5 is of this form. It will imply 7. Is that okay? And now 7 will imply what? 7 will imply 11. Right? And 8 will imply 10. Okay? So if 1 is correct, 5 is correct. If 5 is correct, 7 is correct. 7 is correct, 11 is correct. So it is like you add 4, and then you add 2. You add 4, you add 2. On the other hand, if 2 is correct, 4 is correct. 4 is correct, 8 is correct. 8 is correct, 10 is correct. So it is this time you add 2, you add 4. You add 2, you add 4. And then you will easily check that, okay, for every 6 numbers, okay, for every 6 numbers, it forms a cycle. Okay, so so every 6 numbers, so this is 1, 2, 3, 4, 5, 6. Okay, so 1, 2, 3, 4, 5, 6. We cannot cover 3 or 6, but then we can cover 1, 2, 4, 5. After we get 1, 2, 4, 5, then we will get 7, 8 here as a starting point. So in that case, 7, 8, 9, 10, 11, 12, of all these 6 numbers, those that are not multiple of 3 will be covered. And then for this one, it goes on forever. So that means that all the numbers which are not multiple of 3 will be covered. Is that okay? Can you see this? So it is not like the... So this is of a very strange form. 3k plus 1 will imply not 3k plus 4. Normally, you will add 3. You will add 3 to this. But this time, you add 4 when it is 3k plus 1 type. And when it is 3k plus 2 type, you add 2. But still, it works. Okay, it works. So let's take a normal one. This is the normal case. So if you want to show all the multiple of 3, all the numbers which are not multiple of 3 are correct, the natural way, so we call it the natural way, is 6, 5, 6, 7, 8 is 1 implies 4, 4 implies 7, 7 implies 10, and so on and so forth. Each time you jump 3. And then 2 implies 5, 5 implies 8, 8 implies 11. So each time you jump 3 positions. Is that okay? But here we are doing a little bit different. Okay, instead of jumping 3, 3, we are jumping 4, 2. We are jumping 2, 4. Is that okay? But then it still cover. Okay, it still cover. It's like you switch these two. You switch these two only. Okay, so 1 will not imply 4, but implies 5. 2 will not imply 5, but implies 4. Okay, but after that, 2 still goes back to 8. 1 still goes back to 7. So it is the same as before. So I hope you understand. Okay, let me take. Okay, let me check. If you understand what I'm talking about, could you please raise your hand? Okay, excellent. If you still don't understand what I'm talking about, could you please raise your hand? Okay, very good. Don't be shy. Yes, this is important. So, so let's see if there is a way to explain. So, okay, how about this? Okay, we can look at this as 1 will imply. So if you believe this formula is true, then you will know that P1. If P1 is true, if you believe the orange arrows, P1 implies P7. Does that make sense? Is that okay? Yeah, because I will later show that P1 is true implies P5 is true. P5 is true, then implies P7 is true. So by what? By this hypothetical syllogism. So we will have P1 implies P7. Is that okay? So we have P1 implies P7. We also have P2 implies P8. Is that okay? We will also have P4. We now know P4 is true. Then P4 is true implies P8 is true. And P8 is true implies P10 is true. Is that okay? So P4 implies P10. And we also have P5 implies P11. Okay, if P5 is true, then P7 is true. If P7 is true, then P11 is true. Is that okay? So what I'm claiming is that if a number is of this form, 6k plus 1, then we will have P6k plus 7. Is that okay? Is that okay? And then if a number is of this form, P of 6k plus 2, then I will have P of 6k plus 8. Is that okay? And then I will also have, if a number is of the form P6k plus 4, then I will have P of 6k plus 10. Okay, and finally, if a number is of the form P6k plus 5, then it will imply P6k plus 11. Okay, is that okay? So 1 implies 7, 7 implies 13, 13 implies 19, 19 implies 25. So every number, if you add 6, it is okay. If a case is correct, then you add 6. And then what we don't care are the cases of P6k plus 3 or P6k plus 6, right? But these are exactly the cases where the number is a multiple of 3. So we don't care. Does that make more sense to you? Okay, so 1, if you don't take a very short one, 1 will go to 7, 7 will go to 13, and so on and so forth. 2 will go to 8, 8 will go to 14, and so on and so forth. 4 will go to 10, 10 will go to 16, and so on. And then finally, 5 will go to 11, 11 will go to 17, and so on. So you will see that all the numbers that are not multiple of 3, they are covered. Okay? So if you have any number, let's say, which is not a multiple of 3, let's say 100. So why is the case P100 correct? Okay, we know that if P94 is correct, then P100 is correct. And we also know that if P88 is correct, P94 is correct, and so on and so forth. So we do this, and we will see that if P4 is correct, then P10 is correct. P10 is correct, P16 is correct, P16 is correct, P22 is correct, and so on and so forth. So in that case, using this sequence, you can see that P100 is correct if P4 is correct. Okay? 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 So this is the case. Now, if we are using this, the best way, it seems that we are going to show 4 base cases. So P1 will be the base case, P2 will be the base case, P4 will also be a base case, and then P5 will also be a base case. Is that okay? Okay, but here, if you believe what I'm showing here in the orange one, we just need 2 base cases. So this one, P1 is a base case, P2 is a base case. Because once you have P1, you have P2, then you will have P4 and P5. These 2 are given to you for free. Okay? Now, let me show why this is correct. The proof is quite simple. Okay? So let's look at a special case. Okay? So this is a very small case. So let me call it an L shape. So there's 3, there's 1 here. Okay? Now, suppose that this one and this one, okay, just suppose that this one is empty, so you can use this one to play some pack. So I can jump this over here. Is that okay? Imagine. Then this one is gone and this one is here. Is that okay? And then I can jump this over here. This is the next step. So this one is gone. Is that okay? Is that okay? So this is step 1. This is step 2. And this one is here, this one is here. Is that okay? And then I can jump this back for this step 3. Resulting is, let's say this is the original 3 pieces here. This is the original square here, empty. Then I will have this one left. Is that okay? So you go 1 here, you go 1 up, and then you go 1 back. Is that okay? If you're okay with this, could you please raise your hand? Okay, it needs some imagination. Okay, so this one jumps to this location. So imagine this one is gone. The middle one is gone. And then the bottom one goes up. So there are just 2 left. And then this one goes back. So after that, the effect is all these 3 pieces are gone. Is that okay? So when you have an L shape, you can remove these 3 pieces. Okay? Now, let's take a look of 4 by 4. So this is 4 by 4. Okay? It's the 4 by 4. So you can see an L shape here. Is that okay? So that we can remove these 3. How can I remove? I jump this here, I jump this here, I jump this back. Is that okay? Okay? Now, after this 3 is removed, so I can find an L shape here. Is that okay? Okay, so I can remove these 3 pieces. Is that okay? So by doing what? Jump this here, and jump this back. Is that okay? I still have an L shape here, so I can remove this one. Okay? And finally, I can remove this one. Is that okay? So it's like a what? It's like a it's like a circle. So here, from the case of 4 by 4, we can change it into a case that is having just 2 by 2 left. So if 2 by 2 you can solve it, then 4 by 4 you can solve it. Is that okay? So that's why we have P2 implies P4. If P2 is okay, then P4 will be okay. Let's take a look of a 5 by 5 case. So this is a 5 by 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then finally 1, 2, 3, 4, 5. Is that okay? 5 by 5. So 5 by 5, how do we do? So I have an L shape, I can cancel this one. Is that okay? Is that okay? Now these 3 are gone. Then I will still have an L shape here. So I can remove these 3. Is that okay? If you are okay with this step, could you please raise your hand? Okay, excellent. Now I have an L shape here. I can remove these 3. And then after this one is gone, I still have an L shape here. You see that? So I can still remove this one. So I can remove these 3. I can remove these 3. I can remove these 3, and I can remove these 3. So what do we get? We get 1 left. So if P1 is correct, then P5 is correct. Because we can change the case of 5 by 5 into 1 by 1. Is that okay? So imagine, in general, you have a case of 3k plus 4 by 3k plus 4. If it is a 3k plus 4 case, then what are we going to do? So we are going to cancel 3, 3, 3, 3, and then there's 1 left, 3, 3, 3, 3, and there's 1 left, 3, 3, 3, 3, and there's 1 left, and then 3, 3, 3, 3. Is that okay? So if it is a 3k plus 4 times 3k plus 4 case, then we can remove the outer surface, and then we are left with a 3k plus 1 case. So if a 3k plus 1 case can be solved, then we can solve 3k plus 4. So that's why we have 3k plus 2 plus 2 it should be. Yeah, because we are removing 2 out of 3k plus 4. So is that okay? And similarly, if we have a case that has 3k plus 5 times 3k plus 5, then what we are going to do is, because it is a multiple of 3 plus 2, so we have 3, 3, 3, 3, and then there are going to be 2 left here. 1, 2, 3, 3, 3, 3, 3, 3, 3, and then we have 3, 3, 3, 3, and then we have something like this. Is that okay? So we are removing two circles, 2 peels. Okay, it's like an onion. And then this is a case of 3k plus 1. Is it okay? In the middle. So if 3k plus 1 can be solved, we can solve 3k plus 5. Okay, is that okay? So that's why it's okay. So go through your mind. Okay, so here, this is what I want to demonstrate. It's not just this puzzle. What I want to demonstrate is that there is no particular form of induction. As long as you can show all the interesting cases can be covered, then it is okay. So here, it is not like 1 goes to 4, 4 goes to 7. You can have something twisted. So 1 goes to 5, 5 goes to 7. It is still okay. As long as every number that you want to cover is covered. Okay? Okay, so this is the first example. Okay, now the second one that I want to show is I'm going to use induction to give you something that is nonsense. So I'm going to give you a strange proof, okay, of something which is wrong.